Hello everyone. So today we will study about the chemical bonding and the molecular structure in detail. So let's start. First, the disclaimer slide, which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathi@iitk.ec.in and we shall remove the images. So, this is the index of our today's lecture, in which we have majorly depicted our topics which we were going to study. So, bond parameters, concept of hybridization, coordinate bond, dipole moment, Fajan's rule, formal charge, hydrogen bonding, effect of hydrogen bonding, ionic or electrovalent bond, lattice enthalpy, metallic bonding, molecular orbital theory, resonance, Valence Bond Theory, and lastly VSEPR Theory. So, let's start. First, we will study about the bond parameters. So, the covalent bonds are characterized by some parameters which are as follows. First is bond length. So, in general, the average distance between the center of nuclei of two bonded atoms in a molecule is known as bond length. So, in a molecule, the distance between the center of two nuclei is known as bond length. It depends upon the size of atoms, hybridization, steric effect, and resonance. Usually, bond length of polar bond is smaller as compared to a non-polar bond. Bond length increases as the size of atom or orbital increases. Second bond parameter is bond enthalpy. It is the amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state. And bond enthalpy is directly related to the electronegativity and inversely related to the size of atoms and inversely related to the number of lone pairs of the electrons. Direct related means if bond enthalpy will increase, the electronegativity will also increase, and inverse related means if the bond enthalpy increases, size of atom will be decreases. Okay. Third bond parameter is bond order. So bond order is just like number of bonds between two atoms in a molecule. So bond order is inversely related to the bond length and directly related to the bond stability. So bond order is directly related to bond strength. Stronger the bond, larger will be the bond dissociation energy and bond enthalpy. In the example of CO3 2 negative, you can see here in this diagram, the bond order is directly proportional to the bond strength, right? Let's move on to next page, that is bond order will be equal to 1 plus number of double bonds divided by the number of delocalized position. So for O3 molecule, bond order will be 1 plus number of double bond will be 1 divided by number of delocalized position will be 2. So it will be 1.5. So bond order will be 1.5. For SO4 2 negative ion, the bond order will be 1 plus number of double bonds 2 divided by number of delocalized position is 4. So 1 plus 2 by 4, which is coming out as 1.5. So fourth bond parameter is bond angle. It is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or complex ion. So as you can see, this is the molecule of H2O, where oxygen has this lone pair, and the molecule of water has the bond angle of 104.5 degree, right? Moving on to the concept of hybridization involving sp and d orbital. So Pauling was the scientist who introduced the concept of hybridization. It is defined as intermixing of atomic orbitals of nearly same energy and resulting in the formation of new atomic orbitals, same in number and identical in the all respects like shape, energy, and size. sp2, sp3 hybridizations of atomic orbitals of beryllium, boron, carbon, nitrogen, and oxygen are used to explain the formation and geometrical shapes of molecules like beryllium chloride, boron chloride, methane, ammonia, and water. There is a note here that the d orbital taking part in dsp2 hybridization is dx square minus y square, while sp3d it is dz square, and in sp3d2 the two d orbitals are dz square and dx square minus y square. In dsp3, if dz square is used, the shape is trigonal bipyramidal, and if in dsp3 dx square minus y square is used, the shape is square pyramidal. In case of third period elements, the energy of 3d orbitals are comparable to the energy of 3s and 3p orbitals, as well as to the energy of 4s and 4p orbitals. As a result of this, hybridization involves either 3s, 3p, and 3d, or 3d, 4s, and 4p is possible. So, important hybridization schemes involving s, p, and d orbitals are as follows. So, there is a table here. This is a table given which have 4 columns. First one is of shape of molecules or ions. Second, hybridization type. Third, atomic orbitals, and fourth is examples. So for the hybridization type of dsp2, the shape of the molecule will be square planar, and atomic orbitals present in this will be d plus s plus p and 2 of p orbitals. And the examples of these type of molecule which show hybridization type of dsp2 will be NiCN whole 4 2 negative, PTCl whole 4 2 negative. Similarly, trigonal bipyramidal having hybridization type of sp3d, atomic orbital of s plus 3 type of p orbital plus d. Examples are pf5 and pcl5. Third structure is square pyramidal, and the hybridization type is sp3d2 with one lone pair, and atomic orbitals are s plus 3 of p plus 2 of d, and examples are brf5 and IF5. And last shape of the molecule is octahedral given here, whose hybridization type will be sp3d2 or d2sp3. Atomic orbitals are s plus 3 types of p orbital plus 2 types of d orbital plus so examples are SF6, chromium F6 3 negative, cobalt NH3 whole 6 3 positive. Okay, so these are the important hybridization types and their consecutive shapes of the molecules. Let's study about now some important examples of the hybridization state. So first one is sp3d hybridization. In PCl5, the two axial bonds are slightly elongated, as the axial bond pairs suffer more repulsive interaction from equivalent bond pairs, right? Hence, axial bonds found to be slightly longer and weaker than equatorial bonds. Thus, PCl5 is more reactive. For example, PCl5 molecule, right? This is the image of PCl5 molecule showing sp3d hybridization. Here, these are the equatorial bonds and these are the axial bonds, which are, which suffer more repulsive interaction from equivalent bond pair. That's why they are longer as compared to the length of the equatorial bonds. Second is sp3d2 hybridization. So, in this, we take the example of SF6. So, 4 SF bonds are in the same plane at right angles to one another and are directed towards the corner of a square. And the other 2 F atoms lie at a right angle above and below the plane of F atoms. So, SF6 molecule is a symmetrical molecule and therefore it is stable and less reactive. So this is the SF6 molecule you can see, in which in a plane there are 4 fluorine atoms present bonded to the sulfur, and 2 atoms are in the right angle of the plane above and below, right? So this is the SF6 molecule showing the sp3d2 hybridization. So the formula for predicting hybridization of central atom and the number of hybrid orbitals is given by x will be equal to half of v plus m plus a minus c, right? So where the v is the number of valence electron of central atom, m will be the number of monovalent atoms that is attached, and c is the cation and a is the anion, right? So x, you can predict the hybridization of central atom by using this formula. So while determining the type of hybridization of the atom, pi bonds are never taken into account. This is the point to note, that when we are talking about the determining of the type of hybridization a molecule has or an atom has, the pi bond are never we have to talk about, right? Pi bonds are never taken into account, but lone pairs are always considered. Or else, in the place of pi bonds, lone pairs are always considered, right? This is a point to be noted. So next topic is coordinate bonding. So the bonding in which one atom furnishes a pair of electrons to the other atom, but shared by both the atoms in such a manner that both atoms achieve stability, is called coordinate bonding or dative bonding. For example, in this reaction, H positive is attaching to the NH3 ammonia molecule, forming N positive H4. That means ammonium ion, right? To in this reaction, this is the acceptor, this is the donor, and we have our molecule compound. So second reaction is this, in which ammonia having lone pair on nitrogen reacting with BF3 and forming a complex compound NH3BF3, in which a coordinate bond is forming. Here the donor is the NH3 and the acceptor is the BF3, and they forming a complex by sharing the number of electrons between them, forming the bond or coordinate bond. The chemical bonds that are formed by sharing of electrons between the elements of almost same electronegativity, or between the elements having less difference in electronegativity, are called covalent bonds, right? So for example, formation of O2 molecule. So this is the O2 molecule. You can see this is the layer structure you can see of O2 molecule. So oxygen has 8 electron in total. So uh, 6 will be the electron number of electron in the outermost shell, so it needs 2 more electrons to get stabilized. So this is how, by sharing the electrons with another oxygen atom, oxygen molecule will form a stable and stability will be showing by the oxygen molecule. Next, covalent bond. So the covalent bond can be of the following 2 types: non-polar covalent bond and the polar covalent bond. If the covalent bond is formed between 2 homonuclear atoms, that is, between atoms of exactly equal electronegativity, the electron pair is equally shared between them. Like example will be H2, Cl2, F2, Br2. They form the bond among themselves, and that means that both the 2 atoms uh, have exactly or equal electronegativity, right? So the electron pair is equally shared between them, and no covalent bond will form. So the covalent bond will form. That will be non-polar. Polar covalent bond. The bond formed between the entities are dissimilar, that is heteronuclear or with different electronegativity, and the difference in electronegativity made the bond polar covalent bond. So the bond formed has partial ionic character, as the electron pair is attracted by more electronegative entity, right? So that's why it will be calling as polar covalent bond. So you can see here, H2 molecule, oxygen has some delta negative charges, and hydrogen has some delta positive charges, because the electronegative difference between the oxygen and the hydrogen is large. That's why they show the polar covalent bond nature. And in the HCl also, the bond between the Cl and H is the polar covalent bond, and it is forming due to the electronegativity difference between the chlorine and the hydrogen, which is more, right? That's why the delta negative charge is coming on chlorine and delta positive will be coming at hydrogen. So the greater the difference in electronegativity, higher is the polar nature. The relative order of electronegativity of some important elements are: so fluorine has the 4.0, oxygen greater, which is less than fluorine, that is 3.5. Chlorine less than oxygen will be equivalent to nitrogen, 3.0. And bromine less than chlorine or nitrogen will be 2.8. Sulfur less than bromine will be 2.5. Carbon equivalent to iodine and greater than hydrogen, its electronegativity difference is 2.1. Let's move to next topic, that is calculation of percentage ionic character. So if we want to calculate the percentage ionic character, what should we have to do? First, Pauling equation. So percentage ionic character will be equal to 18 multiply the mole fraction of A minus mole fraction of B, and this whole power goes to 1.4. So this is the equation of percentage ionic character given by the Pauling. Second one was Hannay and Smith equation, and given by Hannay and Smith. So percentage ionic character will be equal to 16 multiplied by the difference in electronegativity plus 3.5 multiplied by the square of difference in electronegativity between the A and B atom, where Xa minus Xb will be electronegativity difference. Here also I said mole fraction, but this is not the mole fraction, this is the electronegative difference between A and B atoms. Okay. Moving to the next topic, that is dipole moment, represented by mu. So this symbol is pronunciated as mu. So dipole moment is defined as product of magnitude of charge, that is q, and distance, that is d, separating the corners of positive and negative charges, right? So its direction is from positive to the end negative. So mu will be equal to q cross d. In the its unit in CGS system, its unit is dBA, represented by capital D. So the molecule is said to be polar if the net dipole moment of the molecules is not equal to 0. For example, NF3 has lower dipole moment than NH3 because resulting vector is towards the lone pair in NH3, but in NF3 it is opposite of lone pair, which cancels the resultant moment. Comparison of dipole moments of NH3 and NF3. So this is the NH3 and this is the NF3. You can see the lone pair is present in both the molecule, but the effect of electronegativity will be different in both of the molecule. Resultant dipole moment in NH3 will be 4.90 into 10 to the minus 30, which is in coulomb meter, and resultant of dipole moment of NF3 will be 0.80 multiplied by 10 to the power minus 30 coulomb meters. So percentage ionic character of any molecule can be calculated by the dipole moment mu. So percentage ionic character will be mu observed upon mu ionic multiplied by 7, and this will be the answer as we were calculating the percentage ionic character of any molecule, right? Moving on to partial ionic character of covalent bond. So on the basis of electronegativity difference, partial ionic character of covalent bond can be summarized as electronegativity difference between the combining atom if equal to 1.7, then the bond is 50% ionic and 50% covalent. If the electronegativity difference is greater than 1.7, the ionic character in bonds is more than 50%, and the electronegativity difference is less than 1.7, that means ionic character is less than 50%. Next is the Fajan's rule. So what is Fajan's rule? It states that the magnitude of covalent character in an ionic bond depends upon the polarizing power. So the magnitude of covalent character depends upon the polarizing power. Higher the polarizing power, more will be the covalent character. So in general, polarizing power is inversely related to size of cation and directly related to size of anion and size of anions and the charge on ions. So, for example, in between sodium iodide and NaCl, sodium iodide, due to large size of I negative ion, has more covalent character. FeCl2 is less covalent than FeCl3 because polarizing power of Fe2 positive is less than that of Fe3 positive ion, having smaller size and higher oxidation state as compared to FeCl3. So, cation with the pseudo noble gas configuration has greater polarizing power than the than the other noble gas configuration cation. So the formal charge, it is defined as the difference between the number of valence electrons of the atom in an isolated or free state and the number of electrons assigned in the Lewis structure. Formal charge on an atom in a Lewis structure will be equal to number of valence electrons in the number of valence electrons in the free atom minus number of non-bonding, that is lone pair electrons, minus half of number of bonding electrons, right? That is shared electrons. Okay. Now let's study about hydrogen bonding. So hydrogen bond can be defined as attractive forces which binds hydrogen atoms of one molecule with the electronegative atom of another molecule, like fluorine, oxygen, or nitrogen. So chlorine has same electronegativity as nitrogen, but it does not form strong hydrogen bonds due to its large size. And strongest hydrogen bond exists is in KHF2. So these hydrogen bonds are of two types, intermolecular and intramolecular. So intermolecular is a type of hydrogen bond that is formed between the different molecules of same substance or different substance. For example, HF, right? So F and H bond is hydrogen bond. H and F bond is hydrogen bond. So intermolecular hydrogen bonding decreases the volatility and increases the boiling point, viscosity, and surface tension of a substance. What is intramolecular hydrogen bonding? It is a type of hydrogen bond that is formed within the same molecule. It formed within the same molecule. Intramolecular hydrogen bonding increases the volatility, decreases the boiling point, and also decreases its solubility in water. For example, orthonitrophenol, intramolecular hydrogen bonding in orthonitrophenol. You can see that in a molecule, within a molecule, the hydrogen bonding is occurring or forming. So this concept is intramolecular hydrogen bonding. So boiling point of water is more than that of hydrogen fluoride because number of hydrogen bonds formed by H2 is more than that by HF. And hydrogen bonding is strongest when the bonded structure is stabilized through resonance. So what is resonance? We will study this. Effect of hydrogen bonding. So various effects arise due to the hydrogen bonding in the molecules are as follows. Due to polar nature of water, there is association of water molecules giving a liquid state of abnormally high boiling point. So you can see here that this is a structure of water molecule combining with the another water molecule by the hydrogen bonding, right? So actually in water, one water molecule is joined to four water molecules. You can see here that let's suppose this water molecule we are taking. So this water molecule is connecting to this oxygen connected to this hydrogen of this water molecule. This oxygen is also connected to hydrogen of this water molecule, and this hydrogen is connected to this water molecule, and this hydrogen is connected to this water molecule. So we can say that in water, one water molecule is joined to four water molecules, two with hydrogen atoms and one with the other two, other two with oxygen atoms. Thus, the coordination number of water molecule is 4. When ice is formed from liquid water, some air gap is formed in tetrahedral packing of water molecules, and due to this, volume of the ice is greater than liquid water, and thus ice is lighter than water. In other words, we can say that when ice melts, density increases, but only up to 4 degrees Celsius. After this, intermolecular hydrogen bonding between water molecules breaks, hence volume increases and hence density decreases. Thus, water has maximum density at 4 degrees Celsius. So, the effect of hydrogen bonding. In the gaseous state, several polymeric forms of hydrogen, HF molecules exist in which the monomers are held together through hydrogen bonding. A pentagonal arrangement of HF molecule is shown below. You can see here the HF molecule arrangement which held together by the hydrogen bonding. Carboxylic acid dimerizes in gaseous state due to the hydrogen bonding, and the dimerization of carboxylic acid is given below. We can see here this is the molecule of carboxylic acid, this CH3COOOH, and similarly CH3COOH. Okay, so this is the molecule of carboxylic acid. They dimerize due to the hydrogen bonding. Ionic or electrovalent bond. The attractive forces of ionic bond, electrostatic force of attraction, are developed between an electropositive atom and an electronegative atom due to complete transfer of electrons from former to later. It is generally formed between the atoms having large difference in their electronegativity. Formation of ionic bond. So, ionic bond is formed by the complete transfer of electrons from one atom to the other. For example, this is the sodium which has 11 electron, and this is chlorine which has 17 electron. This is the electronic configuration, and sodium have one in their outermost electronic shell, and chlorine has 7 in their outermost electron shell. The chlorine needs the 1 electron to be stable, and sodium needs either 7 electrons or either to lose 1 electron to become stable. So sodium will react with chlorine and donate just 1 electron to the chlorine. Chlorine becomes stable and sodium also becomes stable, and they form a compound known as NaCl, right? So ionic bonds are non-directional and also known as electrovalent bonds or polar bonds. Okay. Thank you.